Hello, my friends. This is Dr. Mohamed Nezami again with another lecture on the area of radio frequency and microwave circuit designs. I work as a freelance consultant. I design RF and microwave circuits anywhere from DC to 35 gigahertz. If you like to utilize my services, please contact me at this number or this email. I basically come in and work remotely with your engineers and staff and draft a program in which I can take your product from concept all the way to fab files and documentation, test procedures, and so on, and produce boards. I do the design at the concept level, system level, simulate, model, verify, and then also create the circuit models and finally do the PCB fabrication files for you. And then working on to testing and verifying and doing engineering change orders if it needs to later on. Okay, so anyway, I have a YouTube channel in which a lot of my lectures are posted here. So you can please go ahead and visit this channel. It's right here, the address. Okay. Please go ahead and see if you could subscribe to the channel and share some of these videos. The videos vary from antenna array feed network design to various models and circuit illustrations. And so if you, I hope you benefit from this. In particular, one of the areas that I have covered is I have a playlist in here created for substrate integrated waveguides. Okay, and these are the waveguides that basically they're planar waveguides. Since the height of the waveguide, the B variable, is in this case is the substrate height, we still can operate with a TE10 mode and produce BCB implementation of a waveguide. Okay. I have produced 4 videos already on the concept of substrate integrated waveguides. You can refer back to them. These are in my channel. Okay, but today I'm going to talk about this new to zoom in on an area where what I'm going to talk about, and the reason I was motivated for this is because I have been reached by several graduate students and engineers, and they had some difficulty with the transition from substrate integrated waveguide to microstrip lines. And as you know, we will talk in a minute, the substrate integrated waveguide, unlike waveguides, okay, they're basically right here. This is the input, that's the output. Now, one of the things that we have to do, we have to somehow attach a connector or reach out to a mimic pin chip on the board. So we eventually, whenever we implement anything in substrate integrated waveguide, we have to get back to substrate to microstrip line implementation. And that basically right there is a transition. And the transition, as I will detail in a minute, here it is, okay? Here's a little illustration of a section of a substrate integrated waveguide, where on each side, we have implemented a microstrip line transition. And basically the transition is really simply, we come in 50 ohm at some point, and then we add a taper line in here to carry out the transition from 50 ohm line to the low impedance, relative low impedance of the substrate integrated waveguide. And so we will come back and talk about this more, okay? So again, I operate out of Jerash, Jordan. My consulting services are very reasonable, very low cost compared to consultants back in the USA or in Europe. All right. Okay, so let's go and dig into the substrate integrated waveguide transition using taper line as matching. Okay. Okay, so just to okay, so let's get back to basics. This session really assumes that you're already familiar with substrate integrated waveguide. But what is substrate integrated waveguide? Basically, traditionally, this is a waveguide. This is a piece of waveguide. And as you can see, this is basically is just a hollow rectangular waveguide with a dimension of A here is the wide section and B, which is the height, okay? And depending on the dimensions, these dimensions, we can determine what frequencies would pass into this. Now, contrary to this, planar waveguide implemented as substrate integrated waveguide basically is a piece of PCB board material which has a substrate in here, okay? And then what we do is we utilize this as a waveguide by putting a bunch of vias in here, which an array of vias on each side, and these will create an electrical wall so that this actually behaves as this, okay? And there are some parameters, design parameters to this substrate integrated waveguide. First of all, we start out with a material that you would have picked, like Rogers, Duroid, or whatever, Teflon, whatever, or FR4, that has a substrate with some kind of tangent loss and permittivity, okay? And then we figure out what dimension do we need between the two walls. And that's basically that dimension A here is equivalent to the A in here. It's not exactly the same. It has to be altered from this. We start out with this, and then we can convert from this to this here, as I will show in a moment, okay? And then, of course, the distance between the vias is actually the spacing between the vias, or P. We call it P sometimes, even though this designation here is S. Okay, and then the diameter of the via. Okay, all of these parameters, so and along with the height of the substrate, determines the behavior of this waveguide. Okay, in terms of what modes would propagate, what is the cutoff frequency, how much loss, and so on. Okay. All right, so basically, how do we depart compared to traditional transmission lines? Okay, as you remember, we have the most common one is the microstrip line, just because we have access to it on top, and then we have strip line, which is basically embedded inside the substrate. Okay, with two metal ground planes up on top and on the bottom. And then we have the coplanar waveguide, basically, and all it is just basically a microstrip line that has two adjacent ground channels, okay? And then the bottom one and so forth. So whenever we use this, we have to eventually transition to one of these. And all of these will require us to do a transition from substrate integrated waveguide to a microstrip line. Now, why do we go from here to as opposed to going through these? There are various reasons, okay? Namely, trying to avoid radiations and trying to avoid different modes, the quasi-EM, TEM mode scenario, and so forth. And you can refer to those back in the textbooks or Google some basic paper on the substrate integrated waveguide as opposed to other form of transmission lines, printed transmission lines. Okay, so in essence, what we have the substrate integrated waveguide I borrowed this from IEEE publications, is the best of both in performance between a conventional waveguide, which is rigid, heavy, and not integratable with BC boards, and planar microstrip lines, okay? So let's get to the topic that we are trying to cover. Now, what I'm going to do, I'm going to cover a few videos on this because I couldn't cover the material in one video. It would be long, more than an hour. So I decided to split it into a few ones. Okay. So what we have, here's the substrate integrated waveguide. Okay, with vias with certain diameter and a certain width of the waveguide, which is this here, which is the distance between the vias, the electrical walls in here, and then we have the pitch of the via holes, okay, and that's the P in here, and that's basically what we do. This is really electrical wall, so you can think of this as if you would put a ground wall on here on ground side that connects to the bottom to the top. Except in this case, we can't really plate the manufacturing it would be costly and expensive to plate the edges of this board. Plus, this waveguide would be most times it's in the middle of the board. So what we do, we use what I would call a sampled electrical wall, side wall with these vias. Okay. The only trick is that we choose the distance, the pitch here. We choose it in such a way that the electrical field would not leak out, meaning that this will to the operating frequency that we're at, this will look like is short. We have a cutoff frequency in which none of the electrical field that the signal that propagates this way would leak on the sides, and we would have minimum loss basically. Okay. And this would behave very much like a conventional waveguide, okay, in which you can see of course, the dominant mode is the TE10, where all the electrical field is concentrated in the middle, and it would disappear. To the sides like this, okay. It's sort of like a sinc function or a sine function, half sine function. And pictorially, about this, even though this may not represent the actual what's happening, is we have the macrostrip line, which is basically is really a quasi TEM propagation mode because the electrical field is not propagating only inside the substrate, but rather also in the air on top as well. And where the SIW is like a conventional waveguide, just like this in here, the electrical field is really focused in the middle, is the strongest, and then it would decay to the sides. And so what we need to do, we need to transition from this to this, okay, meaning from this here to this with minimal loss and maximum return loss. So how do we do that? We do that with this segment in here, which is basically, this one is a taper line, which gradually takes the 50 ohm impedance all the way up to, all the way down to the impedance looking into this waveguide in here, okay? And in a moment, we'll see how we do that, okay? So basically, the substrate integrated waveguide to microstrip line matching structure, or the otherwise microstrip line to substrate integrated waveguide matching structure, is represented by this, where the signal comes in with a 50 ohm transmission line, microstrip line, and then we taper out basically to reach down to the impedance, so that the impedance of the taper in here is equal exactly to the impedance looking into this waveguide. Okay, so this taper in here, this tapered line, I'm going to have a whole session on this. Now, even though in a lot of times what we do, just so that we can reduce the development time, we go linear from this point to that point. We just figure out what is the width that has to be here and what is the width that we have for 50 ohm line on this substrate, and we shoot straight just a linear line to these. This would work for most of the frequencies. However, if you really want to optimize this, we have to look at this in terms of taper line matching, which is a whole area that we want to cover. I have a whole session coming up on just in general how to do taper line impedance matching between with 50 ohm to a different, or between input and output impedances. Now, where do you find the substrate integrated waveguide to microstrip line matching structure? I just grabbed these from the publications, available publications, starting out from here, let's say. As you can see here, we didn't use a table line, we used a step line, basically, and that is basically the simplest taper line that you might find, which is basically a transition, a few sections of lines that gradually take the impedance from 50 ohm to the high impedance, in this case of this filter in here. This is a substrate integrated waveguide filter with these cavities in here. And then actually, a lot of times on a BC board, you might have a high frequency 2.9 millimeter connector, like in this case here, an edge connector, that you go from coplanar to microstrip, and then again you want to go to substrate integrated waveguide using this taper in here. So you can see the taper in here. This taper follows a determined function, which is basically either Klopstein transformer or exponential or triangular, and we will go into these. Here's another example that shows how an antenna element is connected to an SIW filter, for example. This is you might think of this as a filtana, okay? And you can see that the impedance, how we went from the antenna impedance to this impedance by actually using the varying these gaps. The length of this gap, the depth of this gap, and the width of this gap controls the impedance looking into this cavity filter, okay? Here's an amplifier where it uses actually the same thing. It uses similar to this, except it's an input-output matching to the microstrip, and it's done with taper lines, okay? Same thing in here. Here's an amplifier where we use the same thing, where the SIW in here is actually transitioned into the amplifier using a tapered line, okay? So all of these, plus hundreds of various different forms that you might find in the publications, where you would integrate a substrate integrated waveguide onto some other section. Okay, so how do we develop the dimensions of the SIW, or substrate integrated waveguide? It's really simple. We start out with a waveguide, rectangular waveguide, that you may choose depending on whether it's a standard or whatever waveguide that you're going to use. It's air-filled, so the epsilon zero in here. And we have the dimensions of the A versus B, and so in this one here, we can transform this actually to a dielectric filled waveguide, just like this, where you have electrical walls on the sides in here. The only difference between this and this is that this one is really filled with dielectric, okay? And of course, for TE10 mode, the height really doesn't matter, because as you know, the cutoff frequency is square root of M, something with M and something with N. If M is 1 and N is 0, obviously N is proportional to is actually the term that corresponds to the height. So therefore, the height in here doesn't really matter. You could still have a height whatever you want and still get the TE10 mode to propagate. So, and then we go from here, since the height is really is irrelevant in this case, we can go from here to a substrate integrated waveguide by doing this, where the height was reduced from B dimension in here to the height of the substrate in here. So the mathematics is really easy to developing the parameters of the substrate integrated waveguide. Basically, we borrow it from, we take a conventional waveguide, we convert it to a dielectric filled waveguide, and all it is just the dimensions are reduced by the square root of the permittivity in here, in this case epsilon r, because in here it's air. Okay, and then we go from here, there's a set of equations that transforms this to this, okay? And here they are, okay? I grabbed this from one of the publications. It's pretty simple, okay? We've got the rectangular waveguide in here. we go down to a dielectric field waveguide. The A dimension in here becomes AD, indicating dielectric. Okay, and then we go again from here, we transform this into a substrate printed planar waveguide, which has the, instead of the AD dimension, it has the AS dimension, meaning ASIW, okay? And the equations are very simple. We start out with the cutoff frequency defined as this for the TE10 mode for rectangular waveguide, okay? And once we have the frequency given to us, because we know what frequency we want to operate at, so we can solve for A. And once we solve for A, we can right away come up with the AD for the dielectric field waveguide according to this equation here. So we just take the A dimension from here and divide it by square root of the permittivity of the dielectric material that is filling the dielectric field waveguide. And then we go from here to a substrate integral waveguide using this equation in here, okay? And all that is basically the substrate width in here, the A dimension of the SIW, is basically the dielectric field waveguide dimension plus a term in here that is basically proportional to the diameter square of the VS, okay? Divided by 0.95 of the pitch number, which is the distance between the vias in here, center to center via, okay? And when we do this, so that means when you do this here, now you still have the diameter and the pitch for the vias, and this in here, in the literature, you can go back to the literature and see how they did this. They say, well, the diameter at least has to be less than 20% of a substrate waveguide length, okay? Or less than lambda g over 5, which is just less than 20% of the wavelength in the substrate. Okay, so that's pretty simple. So we can solve for D using this and then substitute D in here. What about the pitch? The pitch is really has to be less than twice the D in here, okay, the diameter, okay? Because that's really a condition also for fabrication, because obviously we can't fabricate via so close to each other, okay? And once you put that in here, now you have a dimension for AS here. And you can go again. Now, the cutoff frequency basically is the same as you would have for the dielectric field waveguide, except it's really altered by this term in here. And if you want to see how the derivation of all of this, you can, it's really out of the scope of this video. So you can go back to the literature and find that out yourself. There's many papers that derives that. So again, how do we go design a substrate integrated waveguide? We start out with a rectangular waveguide. We have the operating frequency, so we find out what the AD emission is that is needed to propagate TE10 mode at that particular frequency, and then we convert that dimension. We transition it to a dielectric field waveguide by finding out what would take for the dielectric field waveguide, what the width would be in order to operate similar to a rectangular waveguide at that particular, at the A dimension. And that's this basically here. And once we do that, now we need to say, how do we design a substrate integrated waveguide with a dimension, the wide dimension, the width dimension, such that the substrate integrated waveguide will behave exactly like, not exactly, but similar to the conventional waveguides, and that's using this equation here. This equation here proportional to the diameter of the vias in here, and the pitch between the vias in here, the via array in here. And those two parameters in here are basically determined from this relationship in here, okay? So once we do that, we have the AS, which is the width of the substrate integrated waveguide, and that determines what the propagating frequency is, just like we would have for this case. And the cutoff frequency for the TE10 mode is given by this relationship, which is very similar to the conventional rectangular waveguide, except it's deviated by it's we just basically subtract from the width in here this term in here, so that for this to be exactly like this, okay? Now, so let's, right now, as an exercise, what we're going to do, we're going to go to HFSS, and what I did is I said, let's design basically a a rectangular waveguide, okay, that we're going to design, and then we're going to convert that to basically a dielectric field waveguide, okay, which is basically a PCB, okay, a piece of PCB just with top and bottom. And I didn't even need to plate the side walls. So I just left it like this because the length is appropriate so that we can ignore that. And then we're going to go and actually put design a substrate integrated waveguide that will behave exactly the same, okay? So that's what we're going to do. Okay, so what are we going to do is basically right now is do an exercise where we can show how are we gonna design a substrate integrated waveguide for specific frequency of operation, and then compare that to actually how the equivalent of equivalently we have to design this based on the dimensions of a conventional waveguide, okay, by intermediate transition to a dielectric field waveguide, okay. So the first thing we did is I picked up the WR75 rectangular waveguide, which is with these dimensions. That's basically the 19 millimeter by 9 millimeter. Okay, and for this waveguide, the cutoff frequency around 8 gigahertz. Okay, so I'm gonna run this in HFSS and show you how that is done. And then, of course, if conventional waveguide in here, you can actually now, uh, even though we say that the cutoff frequency 8 gigahertz, but we can't operate. That doesn't mean that we can operate at any frequency above 8 gigahertz. Really, it's only valid to certain frequency band where higher than that, the higher order propagation modes will start to play. Okay, and that's what you see in here. Basically, is we check the waveguide for the higher order modes. It turns out in this case, the first one is around 8 gigahertz. The second nearest mode is 16 gigahertz. Okay, and the one after that is 17 gigahertz. So therefore, we can only operate from 8 gigahertz up to this region in here where we can make a requirement that the T210 in this case, the next higher order more than T10 is to be at a certain dB down from the bass band. Okay, now the impedance looking into rectangular waveguide, of course, it's high. It's usually in a few hundreds. In this case, is at 15 gigahertz, 272. Okay, and you can see the impedance, how it changes. Basically, at cutoff, it's infinite, and then it starts to come down, and it becomes flat within the desired operating mode. Next, we designed basically an equivalent dielectric field waveguide, which is basically take a substrate. In this case, I picked Rogers Duroid 5880 with dielectric material of a dielectric constant of 2.2, okay, and tangent loss of 0009. And what I did is I designed the parameters based on this equation in here, okay? So I figured out what the AD has to be. And of course, the height is the substrate height. And then that's basically what I got. So if I do this, I come up with exactly the same cutoff frequency. And the dimension in this case, the equivalent dimension was really 13 millimeters. So a dielectric field waveguide, rectangular waveguide, with the A dimension of 13 millimeter is the same as a rectangular waveguide filled with air that has an A dimension of 19 millimeters. So it's almost half. Okay, so and then after that, of course, if you look at the impedance of this line in here, it's really very low, very low impedance. In this case, at 15 gigahertz, only 22 ohms. Okay. Now, and then what I do next is I programmed this equation in here, this equation in here, to find out what would take for us to put a bunch of vias spaced with a distance of P, the pitch factor, and a diameter of D to operate similar to the waveguides in here. And that's basically what I did is I took this equation and I programmed it in a MATLAB in here. And then, of course, now this in here, really, the rest of this code I will cover in the next sessions. This talks about how you basically transition from a substrate integrated waveguide to a taper line. But in this case, it turns out that the SIW dimension would have to be almost the same, because if you look at this equation in here, if the d square is almost as this factor, so you almost get this becomes tiny, so that almost the AS equal to AD. Okay, and so in this case, I use this here, of course, is basically 13 millimeter, and the pitch factor in this case was a 1 millimeter, which is the distance between these vias, and the diameter of the via I chose as 0.5 millimeter. That's another thing I forgot to tell you. Now, when you come in here and you try to choose the diameter of the via, not only the diameter of the via has to be at least less than 20% of the length of the wavelength at that particular frequency into the substrate, but this has to be manufacturable. As you know, when you're designing a board, you choose a set of vias and you stick to those. You say a via of 5 mils, a via of 10 mils diameter, and so forth. So really, what you can do is you can choose a number for a via. You pick the via size to fulfill this requirement here. And automatically, of course, then you got that, which is basically less than twice that. So you make it P is equal less than a D, equal D, or equal half D, or whatever. And that's basically what I did in this case. The via holes where the pitch between them is a millimeter and the diameter is a half millimeter, okay? And you end up with the same, very near frequency, okay? Same thing almost, okay? Now the impedance, of course, it's very close to the same impedance as you would get from a substrate height dielectric field waveguide. Okay, so now let's go back to the HFSS and just show some of these live. So basically, the first one is we've got this rectangular waveguide. Let me turn this off. Okay, so we've got a rectangular waveguide. Okay, with the dimensions in here, we've got, I have one lid in here, another lid in here. That's where I basically excite the modes. And then I have a vacuum in the middle. Okay, you can see the vacuum. And then I have these sides, basically the metal sides to the waveguide. And the dimensions of this, of course, given by these values in here. So basically, I've got, these are the WR, is it 7.5? I forgot the designation for, yeah, WR 7.5. Okay, so these are the dimensions, which are 19 by 9.5 millimeter, but the width of the height. Okay, so I ran this, and basically this is the S21. Okay, and you can see where the first cutoff frequency is at, and then these are the other modes. Okay, and so the thing that you really want to do, and of course, let's look at the impedance. The impedance around this area is always about 200 and more than 250 ohms. Now, one thing we would want to make sure of is that and this is good for people that are first time exposed to waveguides, and basically what I did is here's this is basically the input port, and you have to set up the number of modes, and let's zoom in and actually let's look at it from the front. So you can see that this is the first mode that we're exciting, and you can see that's basically the mode where the E field is most in the middle, and it goes like a sine mode. And this is the next one, okay? And this is the next mode and the fourth mode. And of course, what we do in this case, as a first mode, really, you would want to make sure that what we're exciting first is basically the first mode, okay? And that's what I have there right now. So you can, in fact, review the E field in here, okay, for the first mode, and that's basically what you get for TE10. Now, you could go in, for instance, and excite the next mode, okay? So, and that would basically to zero out this, and I would excite with this, and let's see this here. And of course, now the reason this is not propagating the next mode is because the frequency is wrong, because the next mode doesn't propagate until M2, which means it has to be more than 15 gigahertz. Okay, so let's see if I solve this for more than 15. This is 19. Oh no, that's the third mode. So if you apply this, there you go. This is the propagation, the second mode. Okay. Okay, and you can go to the third mode and so on. So let's go to the equivalent of this, which is the dielectric field waveguide, and all it is this basically, where I have basically these are the BCB with top and bottom. That's the bottom, and that's the top here. Okay, okay, top in here, and we have an in and out is basically these pieces in here. Okay, and if you look at this now, the S21, let's look at the S21 basically. This is where the cutoff frequency is at, okay? And the E field for this, let's see. Okay, so you can see that's the E field propagating, okay, into this. And lastly, we can go to the equivalent substrate integrated waveguide. So I have basically, in this case, I have the vias that are plotted in here, okay? And so I've got the top and bottom, basically the top and bottom of the BCB. I've got the vias, and of course the vias, you would draw one via and you replicate it basically at a certain pitch factor with a certain number to cover up for these. And that's basically done in here. As you can see, the total number is 42 vias at 1 millimeter distances placed. And then you would duplicate that to the other side again, which is basically a certain dimension twice. That means I duplicated this line here all the way to here. And in this case, if you run this, you end up with this basically is cutoff frequency. The impedance and that is this here, okay? And if you want to take a look at the E field, this is the E field at what frequency? Let's see what frequency I have in here. This is 13 gigahertz, okay? And just to view animate this so you can see how it propagates, and none of the E field leaks out between the vias. Okay, so you can see that it's a BCB with a thickness of 0.5 millimeter, I think. And you can see that the V is in here. The E field is not really going beyond the V's, okay? So you can see that clearly how it's behaving, okay? It's behaving exactly like a waveguide, okay? Except the wavelength is a little bit different. And that's clear from the, because I have the same length piece. You can go back to the waveguide in here and the E field into this waveguide. You can see, oh, I'm still at the different, let me change back to TE10 mode. Okay. So what I want to zero this and put this one here. And then, of course, change the frequency as well. Let's see if, well, 13 gigahertz, I didn't do it. So it's done at 10 gigahertz. But you can see why the mins and maxes in here, the complete half wavelength pattern is only, like in this case, a half here, well, a third here, a half here, and a full one here, versus when you go to the other one. Okay, so basically what we did then is actually we went from a conventional waveguide to a rectangular waveguide to a substrate integrated waveguide, and then with an intermediate transition to the direct field waveguide, okay? And we proved that it is exactly the same. So therefore, now what we can do, we can go ahead and start thinking, how are we going to design a transition to this, okay? So because as you know, the substrate integrated waveguide, you still have to attach a connector to it or get to a point where you connect to, say, for instance, the pin of a specific mimic chip, okay, or a passive component. So you still have to come up to transition to a 50 ohm line like this, or whatever impedance it happens to be. So in that case, what we would need to do, we need to build an interface between a TE waveguide, okay, TE propagating mode waveguide with a quasi TEM mode propagating waveguide, which is just a transmission line, not a waveguide, transmission line. Okay, we want to transition between them, and you can see the copper in here is this width, and the copper in here is the specific, in this case, specific impedance of 50 ohm width of a microstrip line. So we need, and that's represented from here, we need to transition to this, okay, with the A dimension in here and the width of the 50 ohm line here. And we do that through the use of a certain taper line that gradually changes the impedance from 50 to whatever impedance it is on this case. And usually that the SIW impedance at this point is usually low, like 20, 25, 19, 18 ohm, 15 ohm sometimes, depending on the parameters of this. So now this transition here has a certain length. The length in here is usually is a multiples of quarter wavelength. So it's either a quarter wavelength in this substrate, or odd numbers, multiples of that. And pictorially, this is what we want to show. So I borrowed this from the IEEE literature. We would want to go from a quasi-TEM mode into a planar waveguide with a TEM mode propagating on there. And to do this, we have to maintain so that we have minimal loss in here and preserve the return loss, okay? So basically, this is what it turns out, what we have to do mathematically. So we have, in this case, let's say that we have a source which is 50 ohm, in this case here, the microstrip line. And then we have an SIW in here with a certain giving impedance that we would know already prior, because we designed this from a waveguide equivalent, okay? And then we have to go in the middle, we have to vary the, do a match that matches the impedance between Z1 in this case, which is the source impedance, to the load impedance, which is Z2, okay? And we do that through a taper line, okay? So just to summarize, okay, so what are we doing? First of all, the taper in this case, which matches between the 50 ohm and the SIW waveguide, is basically able to transform the quasi-TEM mode, which is a quasi-TEM mode in the microstrip line, okay, to the dominant TE10 mode of the SIW, in this case here. This transition is divided to these parts in here, where we have a 50 ohm line, or a source impedance in here, in this case, whatever that happens to be, most likely is 50 ohm, okay? And then the SIW we've got, and then we've got the transition itself, okay? And then we've got a step discontinuity in the between the two, the taper line and this one, so that in this case, this width in here and this length in here is really what we have to find, okay? And that's basically the concept of the next session that I'm doing. So the transition is analyzed, first of all, by considering the substrate integrated waveguide to be a dielectric filled rectangular waveguide having a height equal to the substrate, that's this here, okay? And by modeling the microstrip feed line, this one here, as an equivalent TEM mode, and we found the impedances of both of these sides and equate them, and in that, from that relationship, we can find what that width of the taper on this side is, okay? And so that brings us to the next topic, which is basically how do you do a taper, a transition matching between the some load impedance, this is impedance versus the length of the taper line, to go from Z0 in this case to R load, and that's what we do here. We have a few types of transitions that we can do. We have the step transition, we have the smooth one, and we have a step, okay? In a lot of cases, some people just say they come in and just plug this here, you know, to a few gigahertz. That's not bad. So, and that's basically what we have to do here. We have this impedance in here, which is our load, and this impedance here, which is source impedance, and we have to get from here to here in a specific length, okay? And we do that either by discrete steps, in this case, which is by the multi-section impedance tapering, or by some kind of mathematical function, which in this case, it turns out there are a few of them, namely exponential, triangular, Klopstein, and or we could do a step one using equal lines of quarter wavelength transformer that's based on either Chebyshev or binomial impedance, which we will show in the next session, okay? So basically in the next session, that's what we have to do. We're going to introduce this, and once we do this, we're going to come back to this computer code in here in MATLAB that basically enables you to scoop in all these parameters and come up with this dimension that is the transition dimension here. So basically, I'm going to give it these values in here, and then it's going to come up with the taper length and the taper width, okay? And that's hopefully, I will see you in the next session. So again, this is Dr. Mohamed Nezami, and again, we were covering the microstrip line to substrate integrated waveguide transition using tapered microstrip lines, okay? And today we have introduced the principles of basically how to design the structure and parameters of a substrate integrated waveguide, and it's compared to starting from a conventional rectangular waveguide, okay? And we have detailed basically the parameters of the transition between substrate integrated waveguide and a microstrip line, or vice versa, okay? And we showed that that can be done using the substrate integrated waveguide itself. I showed that how to derive the structures of the waveguide from a conventional rectangular waveguide, basically, okay, with these equations in here. And basically, I demonstrated that with with the use of HFSS, that we went from a rectangular waveguide to a dielectric filled waveguide first, a dielectric filled waveguide and then to finally to the SIW waveguide in here. Okay, so until the next session, I wish you a good time. We'll see you on the next session where we will show how to design do impedance transformation using tapered lines. Until then, I would like to thank you very much for your attention or for the coming in here and seeing my. Please, like I said before, now there are more details on the other videos that I covered already during the past for the SIW. These are in my channel. You can go back to my channel in here and you can go to the playlist, and the playlist will take you to this playlist, which is Substrate Integrated Waveguide Circuits. And I have already 4 videos, including very soon that I will upload the current video in there. It will reside right here. Okay, so thank you very much. This is Dr. Mohamed Nezami. Again, thanking you for watching this video. Please share this video so that we can distribute this and others benefit from this. I would appreciate it. Thank you very much. See you.